So it's a bit tricky. So you're storing a hash of a password to the server, but why not an encryption? I mean, remember, we taught you that encryption is in CPA. Encryption is really the one that hides the password. And that hashing is not in CPA. Yes, hashing is one way, so it's really hard to reverse and get back the password, but it still could leak something about the password, for example, if two passwords are the same, because it's deterministic. So the question is, why not use encryption instead? And we're using hashing here. Sounds very counterintuitive to what we taught you. So actually, encryption and decryption with a symmetric key is pretty fast. So that wouldn't be so much of an issue. It's more about the way it's used. Yeah? Yeah, I need to store the key somewhere. So imagine this. This server has encrypted passwords. And when a user tries to log in, you need to check if they gave you the right password. So you need to be able to decrypt that encryption and check if the password is the same. But then you're going to keep the key on the server too. Well, then the attacker is going to steal the encryption and the key and decrypt the encryption and get the key. Okay, so that's the problem with encryption, is that even though it hides the data very well, the question is, where do you put the key? The server has to have the key to check that the user gave the correct password. So if the server has the key and the encryption, there's no security that the encryption gives you. Whereas with the hash, it's different, because the server can store the hash of the password for each user A using a cryptographic hash function, right? So something like this. The hash is a one-way function, so it should be hard to reverse it when the attacker steals this hash database. It should be hard to reverse the hash and obtain the password. But then you also have the functionality you want, because when Alice logs in with the password W and provides W to the server can compute the hash of W and check for equality with the hash in the database. Okay, so the server takes the password that Alice applies, computes the hash of the password, and checks it against the one the server has stored in the database. So then it can grant Alice access. Okay? And ideally, if Alice chose a random password, then you can't reverse the hash. It's one way. So if an attacker stole this database of hashes, they won't be able to tell what Alice's password is. But there are some problems with this. The problem is that users don't choose random passwords. And even though any one hash is the hash is one way, you can try different passwords and see if they match the hash. Okay, so that's not breaking the one-wayness of the hash function, it's just breaking the fact that you can enumerate the hash functions because the user doesn't choose random hash functions. So this is an offline password guessing attack. So it's called a dictionary attack. So a dictionary attack is whenever you try all the possibilities in a dictionary. So let's say we have an English dictionary of size D, and n is the number of hashes of passwords. What the attacker can do is, for every hash of a password, really hashes every word in the dictionary and sees if it matches the hash. If it matches the hash, the attacker guessed the password. Okay, so this is called a dictionary attack. And it's another class of attacks that's very common in security. They show up in many, many different settings in different forms. The idea is that you're enumerating elements of a dictionary to see which one works. So is it clear why a dictionary attack would work to reverse, basically, to guess what's the password inside the hash of a password? Okay, great. So there's multiple studies about the fact that people use very weak passwords, and there's a study showing that with a dictionary of only 2 to the 20 passwords, you can guess 50% of the passwords in a high-profile system. Okay, and 2 to the 20 is not that much. Okay, so take a hash of a password, cycle through 2 to the 20 options, and you're going to be able to decrypt half of the, reverse half of the hashes in a database. This is on average across different sites that were compromised. This was the case. And in fact, there's tools out there that created a list of these common passwords, to the 20 of them, and you can use those tools and try to see if you can reverse the hashes from a site you compromised. But I'm arguing that there is an even simpler attack the attacker can do. So if n is the number of hashes of passwords, and d is the size of the dictionary, I'm arguing that there is a strategy for the attacker to mount the attack in less than d times n tries. Do you see how the attacker can do less than d times n tries to basically do a dictionary attack on all these n hashed passwords? Exactly. Yeah, so basically you can do just one brute force scan for the whole dictionary, only one. And then you build a table of hash of password to password. So you try all the 2 to the 20 passwords in the dictionary, and you compute their hash, and then you just store a table like this. So far you don't touch the n hashed passwords you want to compromise. So far you don't do anything with them. You literally just look at your dictionary D and compute the hash for every password and map it to the password. Now you're going to pass over the n hashed passwords and simply look up if they show up in this dictionary, okay, in this mapping. So for every one of the n hashed passwords you want to crack, you're just going to look it up in this mapping if it shows up or not. Okay, so the amount of effort you did is d plus n, because in d time you constructed this dictionary of reverse hash password to password, and then in time n you went over the n passwords. Is this clear? And this is what attackers do. This is called an amortized password hashing. So, for example, LinkedIn was compromised, and the attackers managed to steal 6 million hashed passwords. LinkedIn was storing the hash of the password directly, and were able to reverse many of them, because it turns out that one of the most common passwords were link, that people used for LinkedIn, work or job, right? And God, the angel, and Jesus were also the top. And, and then 1, 2, 3, 4, 1, 2, 3, they were also really top. Okay, so these were in the top 15. So people do choose, many people choose weak passwords. So then, with just this dictionary of common passwords, you can crack, many of them once you were able to steal the list of hash passwords.